Okay, so get ready for a deep dive today. We're going to be exploring how AI is, changing the game for chemistry. Specifically, how scientists are using it to run experiments virtually.
It's like having a chem lab, but it's all in the computer, It's called in silico.
Yeah, in silico, basically running reactions, testing out materials, all that jazz, but digitally. And the cool thing is we're diving into a scientific review, which is awesome for getting a big picture view, right?
Right. It covers a ton of recent research on this.
Perfect for a deep dive. But before we go too far, I gotta be honest. Chemistry always felt, really hard to me. Is it really as tough as it seems?
It can be. Even for, the experts. It's kind of like trying to understand a language, but the rules keep changing on you.
Okay, that sounds frustrating. What makes it so complex?
Well, at the core of it all is quantum mechanics. It boils down to this thing called the Schrödinger equation.
Schrödinger equation, right. That's the one with the cat, right? The whole cat in the box thought experiment. Honestly, quantum mechanics always felt a bit like magic to me.
Yeah, it's definitely out there. But basically, this equation should be able to tell us how electrons behave within a molecule. But it's crazy hard to actually solve. Imagine trying to predict, the exact position of a hummingbird's wings while it's, buzzing around.
So you're saying it's nearly impossible to track all those tiny movements?
Exactly. Especially for anything more complicated than just a handful of atoms, even supercomputers struggle with it.
Wow, okay, so that's intense. So if it's that difficult, how do chemists even get anything done?
They've found some pretty clever workarounds. One big one is called density functional theory, or DFT.
DFT, okay.
Yeah, it's a mouthful. Think of it like this. You don't need to understand, every single thing about aerodynamics to build a model airplane that flies, right?
Right.
DFT is kind of like that. It simplifies the calculations, makes them doable for more complex molecules.
So it's like a more practical approach. But I'm guessing it still has its limits.
For sure. It's super useful, but it's still a shortcut,
And those limitations, those shortcuts, what do they mean for chemistry? Why does it matter if our simulations aren't perfect?
Well, it means we're limited in what we can study, right? How big can these molecules be? How complex can the systems be that we're trying to simulate?
So it slows down progress.
Yeah. Think about fields like drug discovery or material science. We're always looking for new drugs, new materials, better batteries, things like that. And those are really complex systems.
And that's where AI starts to really shine, right? Offering a way to break through some of those limitations, really transform how we do chemistry.
Exactly. AI is it's like giving chemists a whole new toolbox. And these are powerful tools.
Okay, so we've got chemistry kind of hitting this wall, this computational wall. And AI comes along with all these new tools, and it's okay, we can use these to get around that wall or break through it. So what's the simplest way that AI is being used?
Well, one way is using AI to analyze just massive amounts of data.
Okay, so big data.
Yeah. Think of molecules and their properties. So you're basically feeding an AI like a digital encyclopedia of chemical information.
And it can actually understand all that.
Yeah, so it learns to connect like a molecule structure with its behavior,
So it's almost like, teaching AI to read a chemistry textbook.
That's a great way to put it. Except the textbook is humongous. Millions and millions of data points. And for some things, that approach actually works pretty well. It can predict properties or maybe help identify promising drug candidates, stuff like that.
So it can really speed up the process. But it's not going to replace actual chemists anytime soon, is it?
Right. It's not perfect. One of the big things is it might not always know the why, It can make predictions based on the data, but it might not give you those deep insights that chemists need to really push the field forward.
So it's like having this crazy powerful search engine, but not really understanding the chemistry itself.
Yeah, that's a good way to think about it. And that kind of leads us to another more sophisticated approach. It's called machine learning potentials, or MLPs.
MLPs, okay. What makes that different?
So instead of just looking at the data, MLPs, they actually try to learn the fundamental forces at play, between atoms.
So it's less about memorizing and more about actually understanding.
Exactly. It's instead of just learning the facts, it's learning the language of chemistry at a deeper level.
Okay, I like that. It's learning the grammar, the syntax.
Exactly. And this allows us to do some really cool stuff, like simulate how molecules move and interact over time. That's called molecular dynamics. So we can actually run these virtual experiments and see how things behave under different conditions.
Oh, wow. So you can actually see how the molecules, dance around in this virtual world that you've created.
Exactly. Which means we can study things like reactions as they happen. We can try to predict how materials will behave. We can design new molecules with specific properties.
That's wild. And it seems like it would have huge implications, especially for stuff like drug discovery, right?
Absolutely. You can test out millions of compounds without ever even touching a test tube.
Wow. Okay, so we've gone from AI as like a data analyst to AI as a molecular choreographer, which is amazing. But the paper also talked about how AI it's not just about replacing these old methods, it's about making them better.
That's the key point. It's like giving them a boost, you know?
Okay, how so?
We'll take that density functional theory, the DFT we talked about. Instead of replacing it, AI can actually be used to refine it, make it better.
So it's like taking our model airplane and now we're giving it a jet engine.
Yeah, exactly. You're coming up with better equations, better algorithms, making them more accurate, more efficient.
And that allows you to tackle even more complex problems, things that maybe you couldn't have even tried before.
Exactly. Problems that were basically impossible to solve with just the traditional DFT methods.
That is incredible. So it really is this idea of AI as a collaborator, like a partner in the scientific discovery. But it sounds like it can do even more than that, right?
Yeah.
So we've got AI analyzing tons of data. We've got it like predicting how molecules are going to interact. You can even help improve those classic chemistry methods. But in this paper, there was something about AI that just blew my mind. It was this idea of AI, like actually thinking like a chemist would.
Yeah, it's really interesting stuff. So what if, instead of just being this really helpful assistant, AI could actually tackle those fundamental equations head on?
You mean like solving the Schrödinger equation?
Yeah. The one that, look, we were talking about even supercomputers have trouble with.
I thought that was like the holy grail, the ultimate challenge.
It is a huge challenge. I mean, one of the ways people have tried to do this traditionally is with something called variational quantum Monte Carlo, VQMC.
Okay, VQMC, got it. And just a reminder for those of us who, haven't been studying quantum mechanics lately, how does that work?
Okay, so imagine you're trying to describe a really complex shape, like it's like a sculpture, but you can't actually see it directly.
Okay, I'm with you.
So in VQMC, what you do is you start with this educated guess about the shape. We call that the trial wave function.
So we're basically making a very sophisticated guess about how the electrons in a molecule are arranged.
Exactly. And then, using a lot of math, a lot of computing power, you basically try to refine that guess. You compare it to, like, experimental data or maybe some simpler theoretical calculations.
So you're, like, chiseling away at it, trying to get closer and closer to the real thing?
Yes. Now imagine, what if you could bring in a master sculptor, someone who's seen thousands of these sculptures, and they can help you with that process.
So that's where the AI comes in.
Exactly. Specifically, a type of AI called a neural network.
Neural networks. Those are everywhere now. Image recognition, language translation, everything.
Yep. And they're amazing at recognizing patterns, making predictions from huge amounts of data. So instead of us humans trying to refine that trial wave function, we can actually train a neural network to do it for us.
So we're basically handing the AI a chisel and saying, you do it. You're much better at this than we are.
Exactly. And it's really cool because what we're seeing is that these early results, they're really promising.
That's so exciting.
It is. This approach, which people are calling ab initio ML, it could help us study things that honestly before we could never simulate accurately. New reactions, new materials, all sorts of things.
It's like we're giving chemists this superpower to see the world at this incredibly detailed level.
And understand it, which is just, really exciting.
So much potential.
But, I do have to say, it's still early days, right? These methods are very computationally demanding.
So we need even more powerful computers to really unlock the full potential here.
Exactly. But even with that, it's clear that, AI is completely changing how we do chemistry.
It's not just about, like you said, doing the calculations faster. It's about understanding the world in a whole new way.
Absolutely.
Designing new things. Medicines, materials, who knows what the future holds. This has been an amazing deep dive. Thank you so much for sharing all this incredible research with me. It's been eye-opening. And for everyone listening, you want to learn more, we'll have links to some of the studies we talked about in the show notes. Until next time, keep exploring.